So the title of the talk is structuring applications and how to stay sane as your app grows, or at least a way I found to stay sane as my apps grow. And I'd like to kind of introduce the concepts and ideas that helped me through this talk, and then maybe at the end we can have a bit of just open discussion and people can ask questions and share their experiences. So without further ado, first, let's kind of take a step back and think about what really makes projects hard to maintain. Why do we end up in the scenarios where we're not comfortable making changes to a project, or alternatively, right, we're make the changes and we thought we did the right thing, but something wrong happens. And how do we avoid the scenarios? How do we get to the point where we can make a change to a project and be happy with the change and actually have it work the way it was intended on the first try? I think that's kind of a hard problem everybody's struggling with, and there's no one right solution to it. But some of the key things I find that I've identified myself in my work is, one is having shared context. The more things you have to worry about and you have to keep in your head to make a change reliably, the more likely you're going to forget something and then you're going to do the wrong thing unintentionally. And a related problem is with having a lot of branching logic in application, because every time you have a branch, now it's a new case and you have to think about that case. So if you're making a change at the start of a particular flow of events, it can branch out in many different ways, right? And now you have to consider all those ways and how your change is going to affect all those branches downstream. And again, right, we just only have so much mental space in our heads to deal with that. State management is another big problem, right? And I think as Clojure developers, we all kind of know this, that dealing with shared state is difficult. And it's kind of you can kind of see how all those things sort of relate to each other, right? As the general underlying problem is just how much stuff you have to keep in your head and how much stuff you need to know in order to make changes to your application and to be confident that the changes are doing what you intend them to do. And another problem that's sort of related but a little different is that a lot of projects tend to grow through code accretion. So we start a project and we have a set of tasks we want to accomplish with that project, maybe kind of an MVP we're building. And then we build this MVP and we need to make changes to it. We need to add some functionality and so on. And as long as that functionality tends to fit with the original vision and how we structure the project, things tend to go well. But sometimes you end up in situations where it's something you didn't really account for, or your underlying assumptions end up being invalidated, and then you start kind of making hacks. You just add code that solves the problem and doesn't really fit with what you were trying to do originally, but you can't really change your original design at this point, so you kind of just add on to it and add on to it. And over time, you get a lot of the special cases and hacks on top of that original core that was clean, and all of a sudden you're not in a good spot anymore, and making changes becomes very difficult because now you have to consider all those special cases that have been introduced over time. And I think that's a really important aspect of software to keep in mind, is that software is a living thing. It's not a thing you build and put on the shelves and somebody takes and they use it as is, right? As long as your company is in business and as long as your software project is being used, business needs are going to change, user needs are going to change, and it's going to have to evolve. And whatever the original assumptions were that you had when you made the project are probably going to be invalidated at some point if the project lives long enough. So I think it's much more important to worry about being able to make changes to a project and to evolve it than to worry about getting things right up front. And I think this is right, one of the things we see people who prefer static versus dynamic typing often focus on, where static typing proponents tend to focus on this, getting everything right up front and getting a good specification, whereas people who prefer to live in a dynamic world tend to worry less about that and tend to worry more about how do we make a living program. And I think like especially Lisp developers tend to be much more cognizant of that, how to create this runtime that can just keep evolve and live on. So having said all that, let's talk about what do we really want. I think the key part that we want in any software project is ability to do local reasoning. And what I mean by that is, if I'm trying to make a change and say I open a namespace, I want to be able to make changes within the scope of the namespace without having to worry too much about the outside world, right? And like pure functions are a good example of this concept in action. You have your inputs and you do something to your inputs and you produce an output, and that's your contract. That's the only thing you need to worry about. And we kind of want to keep this mindset as the things grow, right? Like we can treat our individual namespaces in the project as sort of microservices, right? Or like individual applications that are structured together. So then when you get into a namespace, you just think about, what's happening within that namespace. And it should have like small boundary that lets you connect it to other namespaces. That's its public API. And this goes to having this clear boundaries between your components. So when you think about your application design and when you're building your application, it's really important to kind of think about it as those isolated units that can be reasoned about individually and can be thought of as kind of like individual programs that just connect to each other at a higher level. And all of this will become important. And the last aspect I think that's really important is knowing the shape of the data. And I think this is something we have to worry more about in dynamic languages, because in a statically typed language, you're going to be forced to describe the shape of your data. You don't really need to like guess what it is. But I think like in a language like Clojure, we often just pass collections of maps around, and we have deep nested data structures that we don't really describe well. So then sometimes, right, like you get an input to your function and it's a map, it has some keys, but you don't really know what they are. And keeping track of that consciously, I think, is important. And again, right, like if you break up your application into smaller independent components, you can kind of describe the shape of the input data at the edges of those components and validate it and so on. And so you know what you're taking in and you know what you're producing back. And then a lot of the guesswork ends up being removed. So let's talk about clean architecture, because this is something I've seen people throw out a lot, especially when people ask about, how do I structure an application in Clojure or any other language, right? And often people just say, oh, you should use clean architecture. And the idea behind clean architecture is nice. We keep side effects at the edges. We have this like pure logic at the core of the application, and then we do this validation on ingress and egress, and everything's great. And on paper, this sounds like a really good idea, and it is. The problem is it doesn't really work in the real world. And let's take a look at why. So what actually happens in the real world for non-trivial applications is that it's very difficult for us to keep side effects at the edges of the application. We need to do I/O on demand sometimes because prefetching can be expensive. Sometimes we just don't know what we need to fetch. Sometimes there could be async workflows where maybe we need to suspend it and get some more data generated somewhere else that we're going to be relying on to continue the workflow. And there's like a million other things that can happen that prevent us from having this nice functional core with imperative shell around. So what do you do at that point, right? Like you can't do this clean architecture. So what happens? And you have this complexity from implicit coupling, right? That's not really solved by clean architecture. For example, if you have a lot of functions that call each other, you have this implicit call graph. And to make changes to the code, you actually need to understand what this call graph is and how it behaves. And this is something that's invisible to us. Like some things we see in the editor, and when we see complexity, like let's say we open up a namespace and we look at the function, and the function looks really large and really gnarly, we go, oh, maybe this should be refactored, because we can see that it's big and ugly and hard to understand. Maybe we can break it up into separate pieces. But when we're dealing with an implicit call graph, we don't see it. It's there, but it's not visible. And it's very easy to create this gnarly relationships in code that we're not really aware of consciously. It's also can be difficult to know what all the valid states of the application are because of that. Because once the application grows to a certain size, you're just not able to keep it all in your head. And at that point, you kind of start guessing. And we see this, right? Like people falling back to stuff like debugging because you can't really reason through all the code. So you just, you run the code and you step through it and you look, what happens at each step. And it's a curious thing because you don't really know that there's just that one path that you took through the code and the alternative paths don't exist that won't have problems. And this all makes difficult to change your code reliably. And then, you kind of try to add some tests, try to reason about it, maybe try to debug it, run through the app, and like at some point you say, it's like, well, it's kind of good enough, and hopefully it works. So with that, I kind of want to lead into talking about different kinds of code we have. And I would argue that there is a few types of things that we do with our code. There is code that does routing, and that expresses kind of an overall workflow in application at a very high level, what we're trying to do and where we're going. And this kind of code doesn't really care about the data that's actually going to be operated on. For example, data that might be displayed to the user or data that we might want to store in a database or send to a different service. It just kind of decides what we're supposed to do with this data. So a good example might be like authentication middleware. You get a HTTP request on your server, and now you got to decide, do you want to forward this payload to the actual handler, or do you want to abort because the user doesn't have permissions to operate on this payload? So the authentication middleware doesn't really care about the content of the request, but it cares where the data should go. And if you look at this code that does the routing, it kind of creates a graph, right? So if you look on the site here, we have like a little diagram, and we can see a workflow that you might see in a payments app. Like let's say you have an app that allows users to send money to each other. And you end up with a sort of workflow where, you try to send money, you might need to check funds. If they have insufficient funds, then you might need to add some funds. If they have sufficient funds, you got to check if the recipient is in the app. And if the recipient doesn't exist, then you have to invite the recipient. And then maybe there is an asynchronous step where now you have to suspend the workflow and wait for the recipient to register and then like do the transfer after. But you also might want to arrange it in many different ways, right? Like maybe you want to check for recipients first, and maybe you don't want to withdraw the funds before the recipient is registered, and so on, right? And you're going to end up seeing a lot of different edge cases if you diagram your workflow out. And I find often like we skip the step and we tend to focus on a happy flow, and then we implement the happy path, and then we start adding different failure states handling a sort of an afterthought on top of it, and that can lead us into trouble. So that's, I think, like one thing that we really need to be cognizant of. And so that's kind of like the routing code. So the other type of code is the data processing code. And this code tends to actually care about the payloads, right? Like, for example, in this graph, the code that's going to actually do the withdrawing of the funds and transfer the funds to a different account is going to be sort of this core business logic for the application. And this code cares about the actual, right, like the values, the amounts we have, the user IDs, and so on. And then we have the I/O handling code that tends to deal with the outside world. And that tends to live also, right, like at the edges close to this routing code, because often when we transition from one state to another state, that's where we need to pull some additional data in. And I think it's worth decoupling these three types of code from each other and being explicit about where each one of the steps happens and why. And I think that the routing type of code is sort of kind of like your outer layer of the code. And within it, you do your IO handling and then the data processing, and then you produce some result and you do something else. And we can kind of make an analogy, I guess, with maybe like a rail network, right? If you look at the rail map of Canada here, we can see there's a bunch of railways and rail routes, and there's stations between these routes. And that's sort of how we can think about our code at a higher level too, where the nodes are the steps where we do some processing of the data, and they're nodes. And these are basically things that happen atomically, and they should be discrete events. And then like once this discrete events happens, we can use the edges of the network to continue to a different state. And the routing should live close to the side effects in this model. And while the implementation inside the nodes in each one of the stations should deal with the payloads and for changing the state of the payload. And then we can keep the implementation pure while the routing and the effects live on top of this pure implementation. So another way to put it is we have those islands of computation. And now we can revisit our clean architecture, because my argument is going to be that the clean architecture is actually, it's useful, but it's a component of a bigger picture. And the bigger picture is this routing flow at the top layer, right? And within this flow, we have a bunch of the small clean architecture islands that can be pure internally and that produce states. And then we can split our application into basically a series of small applications that are self-contained, that are sort of akin to a microservice idea. And the idea is that each one of these applications basically will get the state of the world as an input, do something to that state of the world, and produce a new state of the world. It's a state machine. Like the whole graph, I mean, it's a state machine. And each little application within it ends up being a state handler that takes a big state from the top and produces a new state. And then what we do is basically we get a state, we handle our side effects, like pulling more data or create some effects that we need to create, and then do the computation and produce a new state, and then go back to the routing layer, and the routing layer decides where this current state needs to go after. And so we can see kind of like the relationship between those nodes and the dispatches, how it could work. So the important part is each node should be a discrete step, and it should be an atomic computation, right? So you pass in the state and you produce a complete new state that maybe can be suspended or serialized, and ideally those nodes should also be idempotent, so then you can pass the same state through the system again, and then if it hits a node that already computed the state, it will know what to do. And then we can create boundaries between each steps, right? And like if you go back to the start of the talk where I mentioned about managing complexity, this is kind of what I mean, right? Like I want to be able to do local reasoning within each one of the steps without having to worry about what else is happening in the outside world. And my contract is that I get some state, I do some computation, and I produce a new state. And the size of this node will be kind of like the size that I can keep in my head and reason about without getting confused. And this basically, right, like all this talk effectively brings us to state machines. And I think state machines have a lot of benefits because they force you to think about all the paths that you take through your code and your workflow. And this is what I was talking about earlier, right? That we often just start writing code and we handle our happy path, and then we just kind of like, add the failure states as we go, as they come up. But if you write out a state, if you draw out a state machine, then it will force us to at least consider, like what should happen or what states we can get in. And then it doesn't mean we actually have to implement all those states, but at least we'll make a conscious decision of whether we're going to handle a particular case or not and why. And then if you do want to handle it later, we'll have a clear path of how it should be handled and how it will fit in with the rest of the flow. And creating this complete picture will give us a lot more confidence about what the overall application is doing and why it's doing what it's doing. And it also serves as documentation, because now if a new person, or even yourself after a few months of working on the code, comes back to it, you can see like what's happening and why. And some other advantages that state machine gives us is that you can suspend and restart the state machine, because if you say keep your state in a map, you can take that map and write it to disk, write it to database, wherever you want to store it. Then you can load it up, pass it through state machine again, and everything's happy. It also gives us a lot of inspectability, because if you have these discrete steps in your application that you go through, then you can see the state after each step. And if you get some problems in your application, well, you can be like, okay, we got to the step, here's what the state looked like before the step, here's what the state looks like after the step, here's maybe where we have a problem. And like we all know the benefits of data being Clojure developers, so I have to go too deep into that. And the other thing with state machines is they create an inversion of control. And I talked about earlier how we create this implicit call graphs when we have functions called functions. And then this graph is not really visible to us. And we sort of build it up in our heads as we read through code, right? So I think everyone's familiar with this. You're trying to figure out what the piece of code is doing. You'll find an entry point function, read through it, then it calls some other functions, and you click through and go into those functions and go to those functions and so on. And you're kind of building up this graph in your head as you trace through the code and assemble it in your head. But with a state machine, if you can express these relationships as a data structure, and then you can explicitly say what the state transitions are, where they happen, why they happen, you can document them, and you can see them. And then it saves you a lot of time trying to figure out what the code is doing. So let's think about an ad hoc solution to this problem. One example we could use is to just use multi-methods to chain a high-level flow. And then we'll have one state map where we dump all the work we've done. And then when it goes through multi-method, it will produce a new state map. And we could have a key, like an action or something on the state. So then whenever a multi-method handles a state, it will update the action key, and that will hint the workflow where to go next. And now we can partition all the steps, right, like our application, into a series of these multi-methods. So if we go back to this slide here, we could have, right, like multi-methods for each stage here, and then chain them together by hinting once the stage happens, what action should be taken next. So for example, if, we have a send money, and maybe we have, from and to and an amount we want to send, and then we pass it to check funds, or maybe like the first action is going to be check funds as a key on the map, and then check funds is going to check the funds, and the funds are sufficient, then it's going to update the action to check recipient exists, and if funds are insufficient, could change the action to add funds, and so on, right? So once we build that up, we can create a multi-method like this for handle action, and this is going to be our state, and then we're going to have like resources in the state, and we're going to output a new state. You can implement it like many ways, but this is just like an example. And then we'll have this run workflow, which is the inversion of the control that I talked about, right? Where we just loop through states until we're done. And each time we have an action, we just pass our state to that action to be handled. And now we kind of split out our high-level flow from individual steps. And now we can think about these individual steps in isolation. We can test them in isolation, and we can. But what we can't do is we still don't have the full big picture of how the states relate to each other, right? So that's still opaque to us. So let's take another step, right? Like another natural step would be to express these relationships as a data structure. And we can have a graph, and this graph can be encoded using a map, where the keys of the maps will be the target states, and then the values will be the handlers and the dispatches. And then, right, like we have this inspectability, we provide visual documentation of the relationships in our application. And we have something that can be serialized and loaded and restarted and so on and inspected. And another aspect of it is now it becomes much easier to change order of execution or add or remove states. And this goes back to what you talked about growing the applications through accretion. So often the way we grow applications is we just get a new requirement for a project, we try to figure out where it might fit in, write some code, right? And maybe have a function that used to call one function, call another function that's going to call the previous function and maybe do something else in the process and so on. And we end up creating this complexity that is opaque and difficult to analyze and to reason about. But with a graph approach, we'd be actually creating this explicit states in the graph and then chain them together, right? And now we know that, okay, once we finish this state and we have this output, this thing will need to happen. So let's kind of like take a look at what it could look like. And I'm based on this of a library I wrote called Maestro. And you can check it out after a talk. And I've been using it myself, and I found it to be helpful for me. And, you know, it's not the only way to do it, but it's kind of a way that helped me organize all these ideas. And here is the description of the state machine that Maestro uses. So we have a start state, and a state has a handler, which is going to be a function that's going to take the state map. And then it's going to produce a new state, and there's going to be some dispatches that are the keys in this map. And we're going to check basically the value of the state to see if it has this key on it. And if it has this key, then we go to this dispatch. And because it's vector, it's just going to fall through like a cond. And so this kind of produces a really easy way to organize this graph that we talked about here. And we can literally, right, like once we draw it out, we can translate it to this map here, almost one-to-one. And now the library can do things like check, you know, like if you have the correct keys defined, for example, like, right, like if you're missing a key here, if it's not declared, I can warn you about it. And you can do a lot of the sanity checks, and you can do things like, you know, add interceptors, for example, between your states to maybe do some logging or to produce some side effects that you want to do and so on. But this is kind of like basically the general idea I'm advocating for, to represent your high-level flow as some sort of data structure, such as this map, and then bake in your handlers, which you effectively treat as small applications that do something minimal, another chain together into this flow. And then each one producing a new state in the application. And finally, like, it's worth talking about some challenges and considerations with this approach, because obviously everything has trade-offs. And one thing, like I talked about a lot already, is just figuring out what goes into this map and how to partition your workflow. But I would also argue that's a valuable thing to do in general, so that you can kind of understand before you start writing code, you start getting an idea of actually what you're trying to do, what the steps are, and what the desirable behaviors are, based on the state of the world you know at the time, assuming it's going to evolve over time. You have to be cognizant about separating your computation from your dispatch. So now you really have to think about, you know, like, what is going to be each set of these atomic operations that you're going to do, right? So a really important aspect of using this approach is that each one of these handlers in this map should be an atomic and idempotent thing, right? That you can run many times. So if you produce a state and then you get back, you restart your state machine, you want to be able to handle ending up in the same state and what should happen there, and you don't want to end up like an infinite loop of a state going in the cycle and so on. So like this kind of things that you have to think about that maybe you wouldn't necessarily run into if you weren't using a state machine. There is also potential for visualizing and validating your state graph because it is a data structure, right? Like you can now write visualizer tools, you can sort of graph out what the connections are and actually looks through that. So potentially this approach can sort of act as this living documentation where instead of just having a graph you produce in a separate tool, you can kind of produce this structure and then inspect it and see that the graph that it generates is the graph you're expecting to have. And yeah, I already mentioned the idempotency and restartability of components. And finally, right, like you have to think about what happens with long-running workflows and how you're going to do migrations. So for example, one application I worked with is we'd create this type of workflow, then store it in the database, and then like specifically it was fund transfers. So you start a transfer and maybe like user isn't in the system, so now you have to stop. So you persist your workflow, and then at some point the user registers and you can restart your workflow. But now let's say time has passed between you creating your workflow and restarting it, and maybe you updated the functionality in the system. Maybe now you have like new steps. What do you do? And there's like a few different strategies you can have, right? Like for example, one strategy could be that existing workflows are immutable. So then once you start it, you keep the graph with the workflow, and then you just run through that graph regardless of what happens. Another option could be to do a migration. So then you go through your workflows that you stored and update the steps in them as appropriate. But that's definitely something you have to think about, and that can introduce a challenge that you wouldn't have like in a traditional style application. And yeah, so that's kind of the talk. And I think now I can open it up a bit to questions and discussion.